to pre-calculus honors.
All right, parametric equations. So, look at this situation here. A ball is thrown into the air at a certain angle. The ball, will move through the air, okay? And its position will change horizontally and vertically. So it'll undergo a vertical and horizontal change in distance. And then eventually it'll move up and then it'll move down, but at the same time, it'll also move over horizontally a little bit. All right. Now, suppose you graph each of these changes separately. So you ignore the y and just graph the change in the x, and then you ignore the x and just graph the change in the y, right? So if you graph the vertical distance, this is what it looks like. At time t equals 0, here's where the ball was, right? Because somebody, had their hand up at 40 meters, and they throw this thing up. It goes up as time moves on, and then it starts going down as time moves on, right? That's the vertical distance. The horizontal distance, it just keeps moving away from you as time progresses, so it looks like this. At time t equals 0, it was right next to you. At time t equals 1, it moved away from you. T equals 2, it moved away from you further, and so on. So this is the graph of the horizontal change in distance and the vertical change in distance. Now, on your notes packets, the equations for each of these are reversed. I just changed them here, so just, flip them around. If we come up with an equation for the vertical change in time, it'll look like this. It's a quadratic equation, right? Because it goes up and then it goes down, so it's a parabola. The horizontal, it's a linear change in distance, so this is a linear equation. Do you see that? It's y equals mx plus b. X equals some number t. Okay? Huh? All right, so here we have, just the vertical distance and just the horizontal distance graphed. Okay? Each of them is only part of the entire picture. If we really wanted to graph so that we got the whole story in one graph, okay, then we need to change things around a little bit. So let's just do that. Let's see if we can get the whole story in one graph, okay? What we do is we pick some times t equals 0, 1, 2, 3, and I want to get the x values for that and the y values for that. The way in which I'm going to do that for each of these times, I'm going to plug 0, let's say, into the equation for x. And what do I get when I do that? 0. And then when I plug in 1, I get 30 root 2, which is how much?
Like 40 or 42.
Give me exactly. Right, I just said that. You're supposed to switch them. I fixed it. So when t equals 1, it's 42.4. And when t equals 2, that's 60 root 2. How much is that? And when t equals 3, it's 127.3. All right, so when we plug these values in for y, we get 40. And for t equals 1, what do we get? And for t equals 2, we get? Right? Because it goes up and then it goes down, remember? And for t equals 3, 23.3. All right, now, so at t equals 0, the horizontal distance is 0, the vertical distance is 40, right? Because the guy is holding it, so it's right next to him, but at 40 meters. At t equals 1, it moves away horizontally and it moves away vertically. And this is at t equals 2 and t equals 3. Now, what if we just graphed these? X versus Y. Okay? No. if we just graph these, look, when x is 0, y is 40. When x is 0, y is 40. When x is 42, y is 64. When x is 42, y is 64. When x is 85, y is 60.8. When x is 127, y is 23.3, right? We graph this and we write down the timestamp of when each of these events happen. So at t equals 0, it's at this location. At t equals 1, it's at this location. At t equals 3, it's here. So now if you just look at this graph right here, that literally tells you the entire story. With the x change in the distance, with the y change in the distance, with the time change. Okay? This is when you use different parameters to graph a scenario. Okay? Now, what else can we do? Initially, we had these two equations, right? X is equal to something in terms of t, and y is equal to something in terms of t. Can we combine them and get rid of the t? Well, we can. Can we solve this for t? And plug it in here? We can solve this for t and plug it in here. And what equation do you get? This equation. So now we have two sets of equations, and both of them tells us the same story. These are what we call the parametric equations. They're called parametric equations because they tell you the change in x and they tell you the change in y in terms of t. And then when you combine the two and get rid of t, we get what we call rectangular equations, which just have x and y, just like any rectangular equation would. Okay? So we're not going to do that for this particular problem, but what you would do is you would take this equation, right, and divide by 30 root t, so t is equal to x over 30 root 2. And you plug that for all of your t's down here, and believe me, you get this handy little equation right there. No, we're going to do them. We're going to do that process with different problems right now. Okay? Don't memorize for this specific problem, but we're going to do the process right now. Okay. So what are parametric equations then? This is now a totally new thing for you guys. You've never done this before. Parametric equations are this. If f and g are continuous functions, then f of t and g of t represent a parametric curve. So basically, just like we did before, you get a different set of values for x, you get a different set of values for y, and you graph them. Let's do an example. A parameter is what we call the variable t. And then this is important. The orientation is important. The orientation is the direction over which the curve is traced out. For ones like this, it's easy, right? It starts from here, and you just traverse the curve this way, okay? Most of the time, we put arrows which show you which way the curve goes, and that follows the time. When t equals 0, you're here, t equals 1, t equals 2. Sometimes you get these loops, which may go clockwise or they may go counterclockwise, and it's important for us to know the orientation. All right, let's move on to a real-life example. All right, we're going to sketch the curve given by the pair of parametric equations here. So look, we're going to graph over x and y for different time intervals, okay? And it says, it gives you the time interval. We're going to go from t equals -3 to 3. Okay? So let's do that. You plug in these values into your x and y. So -3, -2, -1, 0, 1, 2, 3. Okay? You plug -3 into your x value and you get 9 minus 1 is 8. You plug negative 2 in there, you get 3. 1, you get 0. 0 gives you minus 1. 1 gives you 0. 2 gives you 3, and 3 gives you 8. We're good? Yes, ma'am. For the other ones, we're going to plug them into the y equation this time. So we get negative 3/4 plus 2, which is 1.25. And then it's 1.5. And then it's 2. Oh, 1.75. And then it's 2. And then it's 2.25. And 2.5. And 2.75. Now, can we graph these? We sure can. When x is 8, y is 1.25. Okay? When x is 8, y is 1.25, so right there. And when does that happen? When t equals what? Negative 3. We write that. Okay? When x is 3, y is 1.5. Where is x equals 3? Y is 1.5. And that happens when t is equal to negative 2. When x is 0, y is 1.75. And that's t equals minus 1. When x is negative 1, we're at 2. And that's when t equals 2. T equals 0, sorry. When x is, where are we? When x is 0, we're at 2.25. And that's when t equals 1. When x is 3, we're at 2.5. Right? And then finally, 8, we're at 2.75. Which is right there. So now you draw your curve. What is it? It's not an upside. It's a sideways parabola, right? So we graph. Now, whoa. This way. Now, your time interval is a closed interval. It starts at negative 3 and it ends at negative 3. So those are endpoints. Okay? And we're going to put in these cute little arrows to tell us the direction of the motion. The direction, the orientation of the curve, rather. Sorry. Okay? So this way. All right? And there you have it. Your very first parametric equation. Now, here it says to write these two equations in rectangular form, right? Rectangular form meaning in terms of x and y only. That means which poor variable is going to get cut out here? T needs to go away, okay? Yep. So what we're going to do is we're going to solve one of these for t and substitute into the other one, okay? So what are we going to do? Which one is easier? It's easier to solve this one for t, right? So t is what? Y over 2, and we're going to plug it into this equation. X is equal to t squared plus 2. X is equal to y over 2 squared plus 2. I just have to say, I love math. And, okay, all right? So x is equal to y squared over 4 plus 2. Okay? And then solve this for y squared.
you have to move the 2 and then multiply the 4?
I meant to multiply this by 4 as well.
Yeah.
Okay, so y squared is 4x minus 8. And how much is y? The square root of 4x minus 8. Now, you can take out 4. So this is the square root of 4 times x minus 2, which means the 4 can come out, right? So it's 2 times the square root of x minus 2. All right? Yes. Okay. All right, so let's go to the next one. One thing I would like to mention is when you take a square root, you don't say positive or negative, right? Because if you look at the equation, the original equation that you're given, y equals 2t, you want your y to be positive, right? You want your t to be positive. So it's all the values that give you your positive y when t is positive. All right. So in example 3, I'm going to give you a few minutes. I'm going to pause the recording for a few minutes. I want you to graph this equation. Okay? So actually, you know what? Let's do it together. Because I don't want you to do it using the chart this time. We're going to put it in rectangular form first, then do the chart. Okay? So, all right, so which one are we solving for t?
X.
All right, so we're going to solve this one for t. That means x squared is equal to t plus 1, meaning x squared minus 1 is equal to t. And now you plug it into the other equation. Y is equal to 1 over 2t. Y is equal to 1 over 2x squared minus 1, meaning y is equal to 1 over 2x squared minus 2. So that is the same equation represented in rectangular form as those two parametric equations. Okay? Now we're going to graph this one. Well, how do we graph this? This is a rational function. We totally know how to graph this. How do we graph it? If you look at this form of it, right? Does this have vertical asymptotes? Remember those vertical asymptotes? Where does this have vertical asymptotes? At one end. At 1 and negative 1, there are vertical asymptotes. Yes? Okay. So we got a vertical asymptote there, and we have a vertical asymptote there. Huh? We have vertical asymptotes. Are there any horizontal asymptotes? This is where the denominator equals 0. Okay? And it's at x plus 1 and x minus 1, right? There are horizontal asymptotes because this is the limit as x approaches infinity of this. Okay? And as x approaches infinity, you have 1 over infinity, which is 0. So y equals 0 is the horizontal asymptote. Okay? We are going to do a whole chapter of limits in chapter 12. Now, if you just pick like representative points, you'll see that the graph is positive in this part. Okay? So if you plug in, for example, x equals 3, right? Is the graph positive or negative? If you plug in x equals 3. It's 1 over 18 minus 2. That's a positive number, right? So the graph lives up here, and you know that that's what it's going to do. If it went up here, then it must go up here. Okay? And remember, your numerator, your denominator, if the denominator was squared like this, then it has to turn back around. Remember? So it turns back around this way. And if it goes down here, then it goes back up there. So listen, you have your graphing calculator with you. Put it in your graphing calculator. But this is how we used to do it. Remember? You can put it in your graphing calculator. So now this is the okay. So this is the graph for it. All right. Now, I know you guys remember, or you miss rather, trig. Here's another one. This is so common in applications, okay? Where you have parametric equations written in sine and cosine, okay? So what we're going to do in this case is, first we're going to write them in rectangular form, meaning only x and y, so which variable gets to be eliminated? Theta. To eliminate theta, when you have sine and cosine, you're going to solve for the trig function. So solve this for cosine and solve that for sine. Cosine theta is equal to x over 3. Sine theta is equal to y over 5. Now, what do we know? Is there a relationship between sine and cosine? Sine squared theta and cosine squared theta equal to 1. So, if sine squared theta plus cosine squared theta is supposed to equal 1, then y over 5 squared, oh my god, look at this. Look at how cool this is. Plus x over 3 squared is equal to 1. Oh my god, what is this? Y squared over 25 plus x squared over 9 is equal to 1. Remember, we always write the x squared first. What is this? What shape is this? Oh my goodness, what shape is this? This is an ellipse. Is this a horizontal or a vertical ellipse? It's a vertical ellipse. How do we know that it's a vertical ellipse? They're both positives. Where is the A? The A for the ellipse is the bigger number, and it's with the Y, so it's longer over the Y than wider along the X. Okay? So this is a vertical ellipse. Centered at where? 0, 0. And how much is A? Come on. 5, and B is equal to 3. No, that's a hyperbola. I know. So, 5 and negative 5. I don't know why I made that so big. And negative 3 and 3. So now look, this is my ellipse. Whoa. Okay, so that's the ellipse. Now we're not done yet because we need the orientation of this. Okay? Now, how do we get the orientation? For that, we need to plug in values of theta. That's right, values of theta. So here's what we do. We go back to the parametric equations. Okay? When theta is equal to 0, where are we? We're here, right? This is when theta is equal to 0. Aye. Okay, when theta is equal to 0, how much is our y and how much is our x? X is 3, y is 0, so we are right there, right? When theta is equal to 0, x is 3, y is 0, meaning at theta equals 0, we're at 3, 0, okay? What if when theta is equal to pi over 2? Right? What's the value when theta is equal to pi over 2? How much is x? X is 0 and y is 5. 0, comma 5. And when theta is equal to pi, how much is x?
What did you ask? Oh, pi, x is
Negative 3 and y is 0. So at negative 3, comma 0. So at 3, comma 0, theta is 0. So here, theta is equal to 0. Here at 0 and 5, how much is theta? And here theta is equal to pi. So what's the orientation of this equation? This way. What happens if you don't put those arrows? Points off. Okay? No. Okay. Yeah. All right. I'll leave out projectile motion for now.